Hello and welcome to a new very interesting video. This video is about this oscilloscope here. It's a Tektronix 2232. I've purchased this recently and unfortunately it is not working. So we will repair it in this video. If you have watched my other videos, you might know that I already have a Tektronix 2230 oscilloscope, and I purchased this as an upgrade to the 2230 because this has better digital storage capabilities. The 2230 has 20 mega samples, this one has 100 mega samples, so this is an upgrade, and it has also the UI is a bit better and the features, so the digital storage, so it's a huge upgrade for the digital storage, but not for the analog mode. The analog is, as far as I know, the same on the 2230 as well as on the 2232. If you are not familiar with this series of Tektronix oscilloscopes, I enjoy them quite a lot because they combine digital and analog in one thing. So with these oscilloscopes, you can switch between digital and analog mode with just one button, this button right here. And this allows me to, as I said before, to switch between analog and digital with the same settings on the knob and so on. And I've always wanted one of these 20-32 because of the better digital capabilities compared to the 20-30. And yeah, finally I got one. Unfortunately not working, but I got one. And this is very great. The cover is also there. I've already removed the cover because it's maybe not so interesting seeing me how to remove the cover. I've also repaired the TDS 460, and in this video you can see how I removed the cover. It's the same procedure, or all these things are constructed quite similar, so it's not that interesting. But I think what's more interesting is to look at it and to see what's wrong with it. So let's do that first. So let's see what's wrong with it. I already plugged it in, and so let's turn it on and see what it does. Okay, it's starting up. There we go. Now we are in analog mode, in pure analog mode. So this switch is on analog mode, and the readings which you can see here are generated digitally, but the trace is completely analog, like in an analog oscilloscope. And maybe you can already see that this is not what it should be, or if I increase the sweep speed, you can see there is a short line moving basically in the wrong direction. And yeah, and on the bottom, if I move the vertical, you can see the line is double, but we are only in the first channel, so this is only one channel is enabled, but we have two lines. And this issue is not only on camera, so what you see on the video is what I see in real life as well. So this is really a problem. So it's not just if you think you see it on the video because of the shutter of my camera. No, it's actually, this is what it looks like. So it's very strange, and we have these two traces, which is very, very strange. And if I enable the second channel as well, so now I have two channels, now it goes absolutely crazy. This is definitely not what it should look like. So if I go to the second channel only, here you can see the second channel also with these double lines. Go back to the first, so we have these double lines here. And interestingly, the digital mode works perfectly fine. So if I go to digital, you can see here we have one line, and it's only one, and it's one solid line, so this works very well. Go back to analog, and we have this strange behavior again. So I'm pretty sure that you're curious to see what a signal looks like on this thing. So I will show you how this looks like. Here I have a sine wave with I think it's 10 kilohertz. Yes, it is. And let me connect this to here. And again, we are in one channel. This is only one channel enabled, and we have the signal is double. It's on the top and it's on the bottom. I can move it that way so that I see only the top thing, and this pattern again is not because of the shutter of my camera, it's just there. And if I increase the sweep speed, now it stabilizes, interestingly, but this is a sine wave, it's just a sine wave. There is no frequency change or period change in this sine wave, but it seems that the sweep, the horizontal sweep, is completely distorted because there it is on a, basically on a, okay, and now it jumps around for whatever reason. Is it touchy? I don't know. It jumps around. I don't know why it does that. And on the bottom we have even more strange thing. But if I go to digital, everything is fine. Digital works perfectly fine. I also tested the other channel in digital mode, the other channels in digital mode, or the second channel basically is only 2 channels. So I tested the second channel and it is working fine, but back to analog, we have this garbage again. Oh, sorry. We have this garbage again, and yeah. So we have to fix that. And before, what actually, and look at that. If I move the horizontal, then it does this strange, basically it looks a bit cool, but this is not what I want. It is, yeah, it's cool, but basically this is not what I want. I want a perfectly fine working oscilloscope and not this strange garbage output thing here. So yeah, we have to look at that. So let me disconnect the signal, and there again we have this strange thing here. Okay, let me turn it off. Yeah, so first of all, I think it's a good idea to look at the schematic of that thing. I already downloaded the service manual, of course. Schematic time, yeah. So this is the section where I will start troubleshooting, because this does a lot of the horizontal stuff, and the horizontal stuff is definitely not working, as you have seen before. So we should start measuring or probing here. So if I zoom in a bit, here we have the horizontal output amplifier, then the horizontal max, which stands for multiplexer, I think, and then here we have the horizontal preamp. So basically this here is the sweep, the A sweep, which is the sweep signal, the ramp signal, which should sweep the trace from left to right in a linear way. And the great thing on these service manuals is that they have provided you or us measurement references or reference waveforms like this here. So we have 51 should be a reference waveform on pin 9 of this chip here. And if I look for again 51, then we should see a ramp, a linear ramp, and there we go. There we have this ramp here. So this is the ramp signal which deflects the trace from left to right, and as you can see, it should be a non-distorted linear thing here. And I think this will be the first thing which I will check, because yeah, it could be caused this issue. But the only thing that I think is a bit strange here is that we had this double traces. If you can remember, we had on channel 1 we thought 2 traces, not only 1 trace. And if this ramp here goes wrong, then of course we could have a distorted x-axis, so the sine wave which we saw, which got compressed and elongated. This could happen. But what could not happen is that it separates the trace into 2 traces. So this is a bit strange. So maybe it's something else. And I also have an idea what this something else could be. But first check this signal. Okay, now I've hooked up my working Tektronix 20 to 30 to test point 51. and let's see what we get. So now I turn on the 20 to 32 and let's see what we get. Okay, this looks good. So the sweep is good. This is a very linear sweep. This is how it should look like. So it should drag the trace from left to right in a linear way, exactly how it should look like. It shouldn't be distorted in some way, like a curve like this or something else. It should be linear, and it is. If I change the time base, it will change, of course. Yeah, this is how it should look like. So the sweep generator is working fine. The sweep is being generated as it should be. So this is not causing the failure. So basically everything before this IC, before this U760 is working fine. So we have to take another look at the schematic and see what else could be wrong, okay? So back to the schematic. Yeah, we already probed at point 51, which is the sweep input of this IC. So the sweep signal is fine. It arrives on at the input as it should be. And this IC actually, it has this sweep in. It has also an X signal input and an XY mode switch input. And what it does, it converts this single-ended input signal to a symmetrical signal. So that's why we have this plus and minus sweep outputs right here. Then they go into this multiplexer circuit, which is actually done with diodes. A bit later on that, I will come back to that a bit later. And here we have the horizontal output amplifier. Actually, this circuit here has a cascode configuration, not cascade, cascode like cathode, and I think they did it to reduce the Miller effect, or to eliminate the Miller effect, so to get a better high frequency response. So basically this is a common emitter circuit, this is a common base circuit right here, and this is how a cascode is formed. So actually we have here this current output from the common emitter, and then it goes into the input of the common base, and then here we have the output of the common base, and at the output of this we have a current source right here, because this base is tied to a fixed potential. So then it acts as a current source, because we set the voltage on this resistor, we fix the voltage on this resistor because of this emitter follower characteristics of that thing. So we can set the current with this resistor, and yeah, this acts as an output, maybe to boost up the output impedance to get more gain. And speaking of gain, we have this feedback loop right here on both sides, and this is to set the gain, I think. Yeah, so it's a bit complicated, but not too complicated. Actually, they are tied together at the same point. So the whole thing here is a differential amplifier. So it's a cascode differential amplifier with feedback in here and with a current source as output. So this horizontal output amplifier is a cascode differential amplifier with current source output and feedback. Amazing. Just amazing. Just to say that is amazing. I have to say it again. It's a cascode differential amplifier with feedback and current source output. Yay. Okay, but I don't think it is broken, so let's not waste more time at this. I think the failure is in here. Why do I think that? Basically, what I think is, again, this thing switches between analog and digital. So what I actually think is that this horizontal multiplexing is not working as it should, because digital mode is working fine, so the output amplifier must be fine. But I think that maybe the switch for analog or so is not working as it should. So let's first figure out how this works. Okay, here we have two inputs for non-storage and storage, so storage on and off. Basically, when this thing is in store mode, then this in store mode, so here, then this voltage here is high, or it's 7.59 volts, which means that this voltage here will be about 7 volts or so. So if this voltage is about 7 volts, then this diode here must be off, because it's reverse biased, because we have 7 volts here and 6 point something here, so it's in the reverse direction. The same happens down here, so this thing must be off. Okay, if this thing here is off, then there is no current from the output of this chip, which is driving the amplifier, but this here, this readings output thing, or this digital output thing here, could be on. Let's see, if we are in storage, then this here is low, this point, so we have 0.53 volts. So what does that mean? If this is low, then this diode is reverse biased, so this diode is off. But the voltage on this point here is, or can be higher at this point, and I think this is a current driven output. We have to look up another another sheet. We have to find this point here, this point 11. Let's see if I can do that for you on a separate window. Of course, I already looked at this thing. Yeah, so let's see. No, there we go, I think. Yes, I was right. So these are these points here, this pin 40 and 41 are corresponding, are corresponding with this. So we have this LH out and RH out. Is it RH? Yeah, RH and LH out. So these 2 points are current driven. As you can see, we have here a differential amplifier, and a transistor basically acts as a voltage controlled current source. So what we see here, it sinks current down here because it's a voltage controlled current source. So here we have current. So in a normal amplifier with voltage output, there would be a resistor up here on which a voltage drop can occur, and therefore we get this beautiful output swing in terms of voltage. But there is no resistor here, so we have the output is current. So it's a transconductance amplifier, basically. Transconductance means input voltage gives output current, and this is what this thing does. Okay, so this differential amplifier, and they have biased it with basically this current mirror here. So this is a matched, or not just a matched pair, it is multiple transistors in one thingy. Basically, is this all one IC? Yes, D, B, A, C. So this is one IC. So these are matched transistors in one IC. Amazing. This is so great. Basically, I love this schematics a lot, because you can learn so much by looking at them. It's just amazing. So let's go back to this point. So again, this is current driven, actually current synced driven, whatever. So current can flow down here if it is in store mode. Okay, so this was store mode. So if we go into non-store, then this is low, this is 0.7 volts. So this means that this diode is off. And if we are in non-store here, then we are high here. So this means that this diode is on, so that the voltage potential here is higher. It's about 7 volts, a bit less, but high enough so that this diode here is off. So if this diode here is off and this diode here is off as well, then the current can flow through this path here via this diode and this resistor down here into the sweep plus, as well as into the sweep minus outputs of this IC. and I'm pretty sure that they are also this open collector thing, so that they are also current driven, because I think that the inner circuit is quite similar. So we have also this open collector going on inside this thing, so that they can draw their current down here. Okay, so that was quite long explanation, but what I will just measure right now is, yeah, basically I will measure these 2 pins. So let's start with this, the first one here. Are they the same? No, we have of course not. We have this here and this here. So yeah, let me probe this point and let's see what we get. I just have to switch between storage and non-storage to see the voltages here, and let's see what we get. So here you can see down here there are these multiplexing diodes, and the first one where I will probe is the CR7303. This is the first one here, and then we have CR7307, which I will also probe. So I just have to find the anode pin of these diodes, because this is the point where the storage enable and disable thing signal comes from. So yeah, let me figure that out and connect my oscilloscope to that. So here I'm probing CR7303. Let me zoom in a bit on this point down here, and now I switch between digital and analog, and yeah, I have to move the camera so that you can see what's going on the oscilloscope. So now I will probe on CR7303, which is here. So now we are in analog mode, and this is how it should look like, because it is mostly on 0 and it goes to high, because basically it's mostly on 0.7, which it should be, and it goes to high because it is because of this multiplexing action is happening between digital and analog. So the analog readings are superimposed to the the digital readings are superimposed to this analog stuff, and that's why it is chopped right here. So if I turn off the digital readings completely, then it is permanently on low. So we just see the analog trace right now, and if I turn off on the digital readings again, and then we can see it again. So let me switch the thing now to storage mode, and in storage mode it's permanently high, and this is what we are expecting. So the signal on CR7303 is fine. Let's go to 7307. Let's go to 7307. Okay, now I'm on 7307 and I'm in analog mode, and I expect it to be 7.45 volts, and it is 0. Okay, so there's something wrong, because it should be high and not low, and if I turn on the digital mode it does not change. Okay, so in analog and digital mode this test point is always low, and it should be 7.45 volts. It should be up here, but it isn't, so there's something wrong. So if I increase the sensitivity to 0.2 volts, you can see it's 0.2 volts in analog mode, and in digital mode it's also 0.2, so it always stays at 0.2 volts. So there's definitely something wrong. So we have to trace down the failure. We have to see what drives this signal. And yeah, so let's do that. Back to the schematic. Okay, we are back at the schematic. Now we have to follow the signal, which is this store L signal, because this was which was wrong. It always stuck at low at 0.2 volts, and it should have 0.53 at low, and of course it should have 7.45 at high if it is high, or if the storage is off, and it never had this 7.45 volts. So it's clearly something wrong with this. So let's follow the signal. It's 4J on sheet 2. So let's see Okay, let me open another one, and we need to find number 2. There we go. And it is 4J. So 4 is here, J is here, and there it is. Okay. So is this... Yeah, store L. So this one is our signal. So this inverter buffer thing has an output on pin 7, and this goes to the signal, and this is what's wrong. So let's probe. So we know that pin 7 of this thing isn't outputting anything. So let's see if we have an input on this IC, and let's see if the IC is wrong or something before it. Okay, so now we have to probe at U7202A. So this must be 2 chips or 2 gates in one chip, I think. Yeah, this is the B. So here we have it. This is U7202 A and B in one, and I will probe on pin 2, and let's see which signal we get on pin 2 of this chip. So pin 2 must be this one here, this one right here, and let's go to the oscilloscope. Okay, now we are at pin 2 of U7202A, and let's turn it on. And now we are... Okay, now it has switched. Aha, okay. There we go. At pin 2, so at the input of this gate, of this chip, we have a signal. And if I go into the non-storage mode, I am in the non-storage mode, it is mostly low, and this chip inverts the signal, so the output should be mostly high. If I go into the storage mode, then the signal is high, which means that the output should be low actually. Okay, so let's do it again. So now in non-storage mode we are low, so we are expecting high. And just to double check, I go to pin number 7. So here we have pin number 7, and the output is our 0.2 volts, and it does not change if I switch between analog or digital mode. Okay, so the input is working, but the output isn't. So the only thing that's left is that the chip itself is broken or its supply is broken. So let me find the supply pin. What will it be? So the V plus pin of this chip is pin number 6. So pin number 6 has how much is this? 8 or something volts. And so this is fine. So the supply voltage is there, the input is there, but we have no output. So what does this mean? That means that our chip is broken. So this IC, this is broken. So we have to get a replacement for it, and let's have a closer look at the chip. So I have to replace this chip. So I found a replacement for the chip. So the original chip was the MH0026, and the replacement which I will use is the DS0026CN. So this is the new one, and this is the old one, the broken one. Okay, so let's see the package. Of course it's the same, it has to be the same. And the pinout is also the same, so it's a drop-in replacement, no extra wires or something necessary. So V plus is here, V minus is here, we have the 2 inverters in here, it's all the same. And of course we have to compare the specifications of the chips, because this is what is important. And let's see, logic 1 input voltage is typical 1.5, and here's also typical 1.5. The logic 1 input current is 10 milliamps, it's 10 milliamps. Logic 0 input voltage 0.6. Input current, okay, what about the output? Logic 1 output voltage It's V minus plus 0.5 volt is typical. Logic 0 output voltage is V minus logic 0. Logic 1 output voltage. Logic 1 output voltage is this one. It's V minus plus 0.7. Okay, and here logic 1 output V minus plus 0.5. Okay, it's a bit more, but this should not cause any issues, I think. Logic 0 output voltage is V plus, so the plus supply minus 0.8 volts. And what do we have here? Logic 0 output voltage is the plus supply minus 0.7 volts. Okay, so this is also fine. And let's see at the timing stuff. Turn on delay is 7.5. 7.5 is right. Turn off delay 12. So this has 11. Or has it? Turn off delay. No, it's 12. Okay, and depending on figure 1 and figure 2. Depending on figure 1 and figure 2. Where is figure 1? Yeah, so they are similar enough, I think, so I can replace them and it should work okay. So yeah, I will replace the MH0026 with the DS0026, and for that, yeah, I have to find a way which allows me to unsolder the chip easily. So let's look at the oscilloscope. Handheld video, yeah. So as you can see, I was able to remove this cover, so I will show you how I did it, because actually it's not that hard. But first a short note, as you can see, or maybe you have seen it already before, there are these white dots on the connectors, and here on the plugs and on the connectors. And to make these white dots, I've used Tipex. Tipex, it's a German product. You use it to remove text. If you wrote something wrong, then you can remove it. It's like the delete key, the analog delete key. So Tipex, okay? It's a bit broken, this one, but it works. And I've used it because I can easily scrap it away afterwards, and so I will not lose a track of which pin is which. Basically, you can also look it up in the service manual, but I do this quite often in recent repairs, so it works quite well. And yeah, how I have removed it, actually you just have to unscrew 3 screws on the top here, then you can remove the top screws, and then you have to unscrew 2 screws on the bottom and 2 words to the bottom screws. This screw is easily to unscrew because it's located here, but the second screw, for the second screw you have to do something different, because you have this beautiful looking thing here. Look at this beautiful thing, it spirals down here. This beautiful thing is the delay line, and the delay line is here there for delaying your signal after the trigger event, which allows you to measure rise times of high frequency signals, and it delays these signals so so they appear a bit after the trigger event, so you see more of your signal. And it's a great thing. And yeah, so first comes the trigger and a little later comes the signal. And this amazing delay line, the most beautiful thing ever existed basically. And you have to take care of your delay line, of course. Take care of your delay line. And the screw which goes into here is under the delay line here. So to remove this screw without removing the whole delay line, it's enough to unscrew it here. So it's screwed down here, so I've unscrewed it here to remove a bit of the tension on the delay line, and then I was able to unscrew the screw under here. But the delay line is very fragile, so take care for your delay line. I cannot say, I cannot iterate enough on that. So take care for your delay line. Delay line, very beautiful. Okay, so but now that this cover here is removed, I have access to this chip, and hopefully I have enough access to desolder it. It's hidden down here. Maybe I can get a picture of it. Where is it? Oh, okay. So the chip is hiding down here. It's a bit dark and hard to see, but this one, there it is, directly above this plug. So I should be able to access it and to unsolder it from the bottom here. So this is the chip. And yeah, I will try this right now with my soldering iron and some of this beauty here, this solder wick. And yeah, let's see how this turns out. So I'll be back soon. Okay, alright, here the new IC is in place. Right now, maybe you can see it down here. This is the new IC. Here we have the old one. It's actually DS0026. And yes, so now it is in place. I will screw this cover back on, or I will just put it back on temporarily, and then comes the moment of truth if this thing is working or not. So let's see. And by the way, when unsoldering this, please be patient, because it is not so easy to unsolder it. Use some solder wick, maybe add a bit of new solder to make a better thermal contact. And be patient that you don't destroy your PCB. Some such things can easily happen. So be patient, be careful when doing this, and of course take care for your delay line. So here's the moment of truth. I've plugged in this board on the side again, and I've also plugged in the power cord. And yeah, let's see if it works. Let's turn it on. I hope so, and I think so. I think that this was the problem. We have measured it, and I don't think there's something else wrong in here. So yeah, let's turn it on. So let me turn off the light first so you can see the screen better. And yeah, let's do it. Okay, fan is coming up and it's starting. Okay, we have a straight line with no distortion, and it's just one single line actually. So this is looking pretty good. Look at that. I can change the time base. Yes, I can. I can make it faster or slower. So this is also working perfectly fine. It seems that we have fixed it. This is looking pretty good to me actually. Okay, so now let's see what it does if we connect it to our function generator. So here I have my 10 kilohertz sine wave. Yes, my 10 kilohertz sine wave signal. And let's see what it does. Shall we? Yeah, let's do it. Let's connect it. There we go. We have connected it to our sine generator, and what we see is a perfect clean sine wave. Look at that. Isn't that amazing? Look at how clear and crisp it is. No weird things are going on with the display anymore. Now we have a perfect clean and clear and crisp sine wave. I can change the volts per division attenuator without any problems. I can change the time base without any problems. I think, yes, this amazing thing has also backlight. Look at that, it has backlight. This is something that the 2230 does not have. So this backlight feature is pretty cool. And the 2232 has it, 2230 does not have it. This trigger is also a feature from the 2232. As you can see, if I change the trigger level, it reflects the trigger level up here, so you can see the trigger level up here. And yeah, but it's working perfectly fine. Let's go to digital. And digital, of course, digital works. Digital has worked before, so it works. And it's also now at the same at the same vertical position, which it wasn't before, because before one part of the waveform was on the top and the other was on the bottom, and the digital was in the middle, but now the digital is at the exact same position where the analog is. Okay, amazing. As you can hear, I'm so happy with that. So this concludes this repair video. So if you have any comments, suggestions or corrections, please write it in the comment section, and please give this video a like if you like it, and I hope you do. And I can say thanks for watching, and take care of your delay line. Bye.